recording. Okay. Now let's continue. First of all, let me compute these two. What we have minus mu dh over dt. Okay, minus mu dh over dt. Minus mu is, well, constant multiplied. H was equal to, H was given as ZAP cosine 10 to 6 pt minus beta x. Okay. Z. Unit vector Z is also constant. That's why it goes out. Dt AP cosine, so AP cosine 10 to the power of 6 pt minus beta x. So if we take the derivative of this expression with respect to time, what we get? Minus, so minus is present. Z multiplied by mu, okay, it doesn't change. A multiplied by P are the constants in terms of time, and the derivative of cosine is sine or minus sine. The derivative of cosine is minus sine. This minus becomes plus. So sine 10 to the 6 pt minus beta x multiplied, and the derivative of the argument is 10 to the power 6 p. Ten to the power 6 p, or better, if we reorganize what we have, Z multiplied by mu multiplied by A multiplied by P squared multiplied by 10 to the power 6 sine 10 to 6 pt minus beta x. Okay, we computed first equation from the previous page. So we have computed the minus mu dh dt. Now next let's compute this one, epsilon dE over dt. So what we have, epsilon dE over dt. So electric field intensity was equal to Y 120 P Y multiplied 120 P cosine 10 to 6 pt minus beta x. One moment, 10 to 6 pt minus beta x. Okay, yeah, it should be fine. Yes, minus y epsilon 1.2 10 to 6 p squared. Yeah, you are right. Okay, if we take the derivative, so epsilon is coefficient, y unit vector y is constant, multiplied 120 p is also constant, and we should take the derivative of cosine 10 to 6 pt minus beta x with respect to time. The derivative of cosine is minus sine, that's why here we put minus. So minus sine 10 to the 6 pt minus beta x multiplied by 10 to the 6 p. Or if we rearrange terms, what we get? If we equal, if we rearrange terms, is equal to minus y multiplied by epsilon multiplied 120 and 10 to the 6 gives us 1.2 10 to the 8. P and P gives us P squared multiplied by, so sine 10 to 6 pt minus beta x. Okay, we have computed these two terms. Now we need to find a rotor of E and rotor of H. So rotor of electric field intensity E equals to, again, we use the method of matrices x, y, and z, d, dx, d, dy, and d, dz. E component of E along x, along y, and along z. So let's see to the value of electric field intensity E. It is given here in the corner. Here you can see, and electric field intensity has only component along y. Has component along y. That's why here the Ez is equal to 0. Ex is also 0. We have component only along y. And if we compute this, what we have, if we take first row and column, we have dy 0. This one is minus d, so minus d ey over dz plus let's take the components along y are 0, dx multiplied by 0, dz multiplied by 0. Okay, and what about components along z? So dx multiplied by ey, so plus z d ey over dx, sorry, and this multiplied by 0 is 0, equals to what? Okay, let me scale down a bit. I will put it here and let me take this and move it here. So okay, first let's take a quick look at the component ey, which is equal to 120 p cosine 10 to the 6 pt minus beta x. It means that ey is a function of x and t. Component along y is a function of x and t. It means that uh, derivative of ey with respect to z will be 0. And we have only derivative of ey with respect to x. And rotor of E will be equal to Z d E y over dx, and this will be equal to Z multiplied. Okay, derivative of this with respect to x will be equal to 120 p multiplied by beta multiplied by sine 10 to 6 minus beta x. Okay. Similarly, the rotor of magnetic field H, magnetic field intensity, rotor of H will be equal to x, y, and z dx, dy, dz, and magnetic field intensity H has component only along z, 0, 0, hz. Okay, and is equal to, if we take x dHz over dy, if we take y plus, or better minus y dHz over dx. Yes, and component along z is 0. And if we look to the hz, which is the hz, okay, equal to a multiplied by p multiplied by cosine 10 to 6 pt minus beta x, and hz is a function of x and t. Again, is a function of a, x, and t. That's why this term is 0, because the if hz is a function of x and t, the derivative with respect to y will be 0, and okay, and rotor, sorry, rotor of h is equal to minus y dh z over dx equal to minus y multiplied a p by beta by sine of 10 to 6 pt minus beta x. Okay, now let's go back to our system of equations. It was here. Okay, we have defined this term, also this and these terms. We have defined all terms. Now we can write the system of equations. So let me copy this and I will paste it here just for the reminder. I will paste it here, and rotor of E was here. Yep, rotor of E is equal to Z 120 p beta. So Z 120 p beta multiplied by sine 10 to the power 6 pt minus beta x equals to, so look, this is this rotor of E, and we need to put this value here, or minus mu dh dt. Minus mu dh dt we computed, I think, here. Yep, minus mu dh dt is this, z mu a p squared 10 to 6. So z mu a p squared 10 to 6 multiplied by sine 10 to 6 pt minus beta x. Okay, now rotor of H. Rotor of H was here, minus y ap beta. So minus y ap beta minus y ap beta sine. Okay, sine 10 to 6 pt minus beta x equals, and finally this term was defined here and is equal to epsilon 1.2 10 to 8 p square epsilon. So okay, one moment. Yep, minus y epsilon 1.2. So minus y epsilon 1.2 10 to the power 8 p square. Ten to the power 8 p square multiplied by, okay, sine. The argument of sine always is the same. We have system of, now we have the system of equations with unknowns beta and a. So first of all, let's look to our system. From the both sides we can simplify sine 10 to the 6 pt minus beta x, sine 10 to the 6 pt minus beta x. Also here we can simplify sine. Also we can simplify the unit vectors z and minus y and minus y. What else? Also we can we can simplify here p and p. Yep. Here also p and p, and simply we have, so I will write in the same page, that's why let me scale down. Now what we have 100 okay, also we can simplify 10 with this, and here we will have 5, or we may not simplify, doesn't matter. So we have 12 beta 12 beta is equal to mu a p 10 to the 5, and next we have a beta, a multiplied by beta equal to epsilon 1.2 10 to the 8 p. So we have a system of equations. It's simple. So mu is 4 multiplied by mu 0. We may simplify to 12 and 4 as well. Here remains only 3. Epsilon is 4 multiplied by epsilon 0. Okay, what we have now? We have beta, which is equal to a mu 0 p by 10 to the 5 over 3, and here a multiplied beta equal to 4 multiplied 1.2. Okay, let me write a little bit more compact in. So 4 multiplied 1.2 multiplied 10 to the 8 multiplied by epsilon 0 multiplied by p. So this is our final system of equations. We take beta or better this beta and put here, and we find a. Okay. So what we have, if we put instead of beta this expression, we have a squared multiplied by mu 0 by p by 10 to the power 5 over 3 is equal to 4 by 1.2 by 10 to the power 8 epsilon 0 p. And okay, it is simple. P and p simplifies again. 10 to the 5 and 10 to the 8 simplifies. Better 8 simplifies. Here we will remains only 3, and a squared is equal to 12. 3 multiplied by 4 multiplied by 1.2 multiplied by 10 to the power 3 epsilon 0 divided by mu 0, or 12. 12 multiplied by 12 multiplied by 10 to the power 2 epsilon 0 by mu 0, and a will be equal to square root of this. If we take square root, we have 12 multiplied by 10, 120, square root of epsilon 0 by mu 0. Okay, if we put numeric values here, what we get? 120 square root of numeric value of epsilon 0 is 8.854 10 to the minus 12, if I'm not mistaken. And numeric value for mu 0, 1.257 10 to the minus 6. Okay, if we compute, we will have something about 0.3185. The value of A is 0.3185. What about beta? Okay, here we define that beta is equal to this, or beta is equal to a mu 0 p 10 to 5 by 3. So beta is equal to a mu0 p 10 to 5 10 to the 5 by 3. Okay, if we put instead of a this value, what we get? 120 square root of epsilon 0 mu 0 multiplied by mu 0 multiplied by p multiplied by 10 to the power 5 divided by 3. Okay, this is equal to this one, and this one simplifies. Here we will have 40. And what we have for beta will be equal to 4 multiplied 10 to the power 6 multiplied by p multiplied by square root of epsilon 0 mu 0. And so if you compute numeric value of this for beta, you will have 0.0419. This is the value of beta. Okay. Do you have any questions? Okay, good. If you don't have questions, wait. Okay, great. Okay, if you don't have questions, we move to next problem. The next problem in our plan is related to the boundary conditions. Okay, can we move to the next problem? I think yes. If we finish five or 7 minutes later, it's not a big problem. Or you don't have time. I think you have time.
Yes, I have.
You need to have time. Okay, there left only 10 minutes. So we'll do one problem. Let's see this problem regarding the interface conditions. So okay, let's read the problem. A time-dependent electric field intensity is applied on a dielectric as shown in figure. Okay, in this figure, the electric field intensity in free space is given as, so electric field intensity E is given as Z multiplied by E0 cosine omega t. Okay, E0 is given. E0 is given as 100 volt per meter. So omega is also given 10 to the 9 radians per second. So epsilon 0 or epsilon r relative permeability, electric permittivity is 25. Calculate peak displacement current density in the dielectric. There is no surface at interface between air and material. So we have here air, and here we have some dielectric material. So in free space. Yes. Here on the left we have air. On the right we have some dielectric material. First of all, let's define D. So this is, let's call it E1. E1. This is the first medium. This is the second medium. Let's call the electric field intensity in the first medium E1, and D1 is simply epsilon 0 E1. Yep. And we go to boundary, to the boundary conditions here. You can see that for electric flux density, we have boundary conditions. This is tangential boundary condition. Okay, let me put it here. And this is normal boundary conditions. So here we don't have tangential components because the axis z is given in this direction, and our electric field has component only on the direction of z. It means we don't have any tangential components. It means the tangential component of electric field is 0. That's why the tangential component of D will be also 0. The tangential component of the D2, okay, we don't know yet. For this we don't know yet. And also is given that there is no surface charges at interface between air and material. It means the surface charge density is also 0. From this we can conclude that normal component of first D1 is equal to the normal component of second D2n, and from here we can write that D2n is equal to D1n and is equal to epsilon 0 E1 normal and is equal to epsilon 0 E0 cosine omega t. This is normal component of the electric flux density in the second medium or in the material. Now we are interested in tangential component, D2 tangential. We don't know yet about the tangential component. Okay, in order to compute tangential component, we use D1 T over epsilon 1 equal to D2 T over epsilon 2. From here, D2 tangential is equal to epsilon 2 over epsilon 1 multiplied D1 tangential. Oh, okay. The tangential this one was 0 and tangential component of D2 also 0. That that is better. Now the D2 electric flux density in the second medium is D1 sorry, tangential component plus normal component. So this one is 0. Normal component is Z epsilon 0 E0 cosine omega t. We are asked the calculate peak displacement current density. So displacement current density was JD, and it was the derivative of electric flux density by time. And if we take the derivative, we have minus Z epsilon 0 E0 multiplied by omega multiplied by sine omega t. And the, okay, and this is, or epsilon 0 multiplied by E0 by omega is peak value. If you put numeric values, you will find the numeric value for peak value of current displacement current density. So the main idea, displacement current density is the derivative of d by time, and derivative we found is equal to this, and this is changing with this is changing in time by the law of sine, or this is harmonic, and the peak value is this, the peak value of current displacement current density. Okay.